First thing I want to talk about is this special function that we call the gradient function, so the function that measures the slope of a curve. That y equals function x, that's our function. We know what it does basically is measures how far away it is from the x-axis, the y value. Well, the gradient function then measures how steep it is at that particular point. So another way of saying it is the distance from the y-axis is changing. That is what's also known as the derivative, and you've probably heard of that term, so the derivative. Now to start off with, we're going to use geometry to find the gradient function, and we can do it quite successfully for things like lines, and semicircles actually work quite well as well. So with a line, it's real easy, because if you've got a horizontal line, well, we know the answer to that already. Horizontal lines have a slope of 0 no matter which point you substitute in. So there's no work to be done there. If I've got a function which is a constant number, so you draw a horizontal line, we know its gradient function must equal 0 no matter what the x value is. And with an oblique line, well, we know all oblique lines can be written as y equals mx plus b, and the coefficient of x measures the slope. So again, I know the gradient function for an oblique line will always be a constant value whatever the slope of the graph is. So those two are real easy. Semicircles, a little bit more work. There's our standard semicircle. So the square root of the radius squared minus x value squared. It doesn't have a consistent slope for the x-axis like the line did. Depending on which x value I pick, I'm going to get different answers for the slope. And the slope of curve we talk about is really the slope of the tangent at that particular point, if we were to draw a tangent. But what we do know is our tangent, which I've drawn in there, so x coordinate is x, y coordinate is whatever we get when we substitute it into the function. But we know from circle geometry that that radius is always perpendicular to the tangent. So I do know that. Well then, that allows me to find the slope of the radius. It's going to be the y value over the x value, rise over run, because that's the slope of the line that's joining the origin to our point. So whatever function x is over x. Now if the tangent's perpendicular to it, its slope is the negative reciprocal. So we got minus x over function x. But we have an equation for function x. We said it was the square root of r squared minus x squared. So therefore the gradient function is minus x over the square root of r squared minus x squared. And we've got a formula for our semicircle. Unfortunately, not all curves are as nice as that. Everything else then we, at this stage, have to estimate using secants. So a secant, remember, a tangent is a line that cuts the curve in one spot. A secant would cut it in multiple spots. So let's have a look at a quadratic. What happens with our standard parabola? Function x is x squared. And let's investigate the point 2, 4. What's the slope of the tangent at that point? Well, if I choose points either side of it then, so I can create a secant. So I've picked 1, 1 and 3, 9. Now if I calculate the slope of that secant, it would be an estimate for the slope of the tangent, because the tangent would be hopefully parallel to it, but pretty close to it. And the slope of that's 4. So I'm saying that when I substitute 2 into the gradient function, I still don't know what the actual function is, but it'll give me an answer of approximately 4. Now how accurate my answer is going to be will depend on where I place these 2 points. That actually turns out to be correct. It is 4. Because I chose those very carefully. I chose them symmetrically. And that works with our parabola here. If I choose them symmetrically about the point, it'll work. So in general, if I have x and then the y value would be x squared, if I pick a point, say h to the left of x and h to the right of x, I create symmetry. Well, the y values would be x plus h squared and x minus h squared. I can work out the slope and we come up with 2x, and 2x is indeed the gradient function for x squared. The hyperbola, for instance, will that same idea work? There's the point 2, a half. I'll pick a point either side of it. Now, if you have a look at that and imagine where the tangent would be placed, hopefully you'd agree with me that doesn't look like it's going to give me a good estimate. But anyway, let's see what happens. If I work out the slope of that secant, it's minus a third. So I'm approximating that the slope of the tangent would be minus a third. No, turns out it's not. It's not minus a third. It actually is minus a quarter. So that idea didn't really work that well for the hyperbola. The other thing that's really important is that the curve has to be continuous between the two chosen points. Let's imagine I choose BC. Well, it's 2 points either side of that x value, but one's on the left branch, one's on the right branch, and we'll just have a look at that green line I've drawn. Hopefully you would agree with me that that would be a terrible estimate for our tangent. So if you have an accurate graph, and that's the key too, you've got to have an accurate graph, then it's usually actually better to draw the tangent in itself and then look at that line and try rise over run. So pick some points on the line and actually work it out. So 9A, I'll put in there, look, don't worry about the sketch for question 9.